Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 1 lecture. I hope you enjoy it.
This is chapter 4.8, and 4.8 is about differentials. Ooh, there we go, differentials. So before we get into what differentials are, let's think a little bit about the equation of a tangent line. So recall that the equation, the equation of a line is y minus y sub 1 is equal to m times x minus x sub 1, right? That's at the given the point x sub 1 and x sub 2. X sub 1 and y sub 1, right? Um, so if instead of doing it there, I did it at the point c comma f of c, well, what would that look like? That would say y minus f of c is equal to m times x minus c. But in calculus, we already know that m is equal to f prime of c, right? The slope of a curve happens at the slope of the curve can be found by the derivative evaluated at that point in the curve. That's what this is saying. So we can say here that y minus f of c is equal to f prime of c times x minus c. Moving this up to the other side, I end up with y is equal to f of c plus f prime of c times x minus c, right? So that's the equation of the tangent line of the curve, right? So now, let's think about what that is on the graph. All right. So on the graph, let's say that I have some curve and I've got this tangent line, right? And we can draw that a little bit better. And we've got this tangent line. There we go. That's way better. Look at that. Beautiful. Now, in here, on that tangent line here, that was y. And here in blue, we've got the function f, right? Now, if we were to take a closer look at this region, right? When the tangent line is very close to the function, right? In other words, very close there to the point of tangency. Well, what could we see there? Well, we would see something like this. Well, let's draw that better, right? That curve zoomed in there would almost look like a line, and then the tangent line would look like that, right? If you notice here, well, so that's the zoomed in version of that, right? Um, if you notice here, this is not that different. The blue line and the yellow line there, I mean the blue curve and the yellow line, they're very close there. They're very similar, right? What do I mean by that? I mean that the y values there would not differ by much, right? Even though the x might be differing by more, right? And the closer or the less that the x values differ, the less that the y values differ, right? And here I'm talking about if we think about x values and y values, right? These x values, the closer the x values get, the closer the y values get, especially as we get closer to the point of tangency. All right. This leads us to the following statement that f of x, and perhaps I'll do it with a color coordination, f of x is approximately equal to um, f of c plus f prime of c times x minus c, right? Near the point c comma f of c. This is called the linear approximation. All right. So this is um, the linear approximation of f at c. All right. Now, why do we care about that? Well, let's think about let's this an example where this linear approximation is important. So let f of x equal the square root of x. Use linear approximation. I said that wrong. Approximation. There we go. Use linear approximation to estimate the value of the square root of 9.1. All right. So we're going to try to figure out what the square root of 9.1 is. Now, we know what the square root of 9 is, right? So let's do this. Consider x equals 9. If I plug that into the function, so f of 9 would be the square root of 9. That would end up with giving me a value of 3, right? So in here, what I'm going to do is I'm going to do a linear approximation. I keep saying that, approximation, linear approximation. There we go. I'm going to do a linear approximation of the function f here at that point. So here, what we're implying is that we're going to do our linear approximation based out of that point. All right, so what do we get? Well, let's see. We already know the formula. The formula was that f of x is approximately f of c plus f prime of c times x minus c. All right, so what does that give us? That gives us now, well, f of c, that's the y value. So we have, well, let's write it this way. F of 9 plus f prime of 9 times x minus 9, right? Those are all our x. Our x value is 9, right? That's why I plugged that in there. Now, in here, the next thing we need to figure out is, well, what's f of 9? Well, we've got that, but we still need to figure out what f prime of 9 is. So let's do some side work. F prime of x. Well, if I think of f of x, I'm going to think of f of x this way. F of x is x to the 1/2, right? That's equivalent to saying the square root of x. The derivative is going to be 1/2 x to the negative 1/2. All right, so I can rewrite that as 1 over 2 radical x. And now if I plug in the x value into there, and then with f prime of 9 is equal to 1 over 2 times radical 9. Radical 9 is 3 times 2, I get 6. So what can I do now? I can say now that f of 9, well, we just said that was 3, right? 3 plus f prime of 9, we just got that it's 1/6, and then times x minus 9. And there we go. That's our approximation. So let's reduce this a little bit. In other words, let's expand so that we can combine like terms. Notice that 1/6 times negative 9 is negative 3/2 because I just reduced the 9 over 6, right? They're both divisible by 3. And from there, I end up with 1/6x plus, well, 3 minus 3/2. So apple minus half apple, half an apple. So I get half of 3. Half of 3. There we go. So there we go. That's my linear approximation. All right. So what we found here is that f of x is approximately 1/6x plus 3/2. Now what? Well, the original question was to estimate the value of the square root of 9.1. So let's find that out. F of 9.1, which would be the square root of 9.1, is, well, according to our approximation, it is approximately 1/6 times 9.1 plus 3/2. All right, so let's reduce this a little bit more. Let's change this. So 9.1. So let's write it this way: 9.1 over 6 plus 3/2. I don't like that 9.1. All right, let's get rid of that. So I'm going to multiply both the top and bottom by 10. So what I end up with here is 91 over 60 plus, well, now I see that I'm going to be over 60. So let's come up with a common denominator. To go from 2 to 60, we multiply by 30. So 3 times 30 is 90. 91 plus 90 is 181. So I end up with 181 divided by 60. All right. So that would be approximately the square root of 9. Excuse me, the square root of 9.1. In here, this actually is approximately, so it doesn't reduce. All right, that fraction doesn't reduce. But this is approximately 3.016666, well, with 6 repeating. All right. and that's actually an exact value because the 6 is repeating. All right, so that's what we get there. But now, that 9.1, that's very, very close to 9. All right, and in here, notice that when I spoke about this, I said it needed to be near our point of tangency. All right, near a point of tangency. So our x values cannot go that far from this point of tangency. Now let's see how good our approximation is. Um, well, hold on. Before I move on, the square root of 9.1 is actually exactly equal to 3.016620626 with a whole bunch of other stuff. All right. Notice that's pretty close. 3.01660166. It's only after that it starts differing, right? But anyway, so I was saying, let's see how good our approximation is for values that are a little bit further away from 9.1, from 9, excuse me. So for example, let's figure out what happens when I plug in 10. So the square root of 10. The square root of 10, well, according to approximation, will be approximately 1/6 times 10 plus 3/2. All right. At that point, well, let's see. I end up with 10/6 plus, to go from 2 to 6, multiplied by 3. So I end up with 9/6, giving me 19/6. Now 19/6, if you plug that into the calculator, we end up with 3.16 with a whole bunch of sixes afterward, repeating forever. All right. The square root of 10 is actually equal to 3.1622776 with a whole bunch of other stuff. But look at that. 3.16 and then an extra 6, 3.16, and then it changes, right? So that's a pretty close approximation. But again, 10 is not that far from 9, right? Let's figure out what happens if you go really far from that. So for example, let's see what happens if I try to use that approximation with 64. All right, so the square root of 64. According to our approximation, right, it was 1/6 times 64 plus 3/2. And this ends up becoming 64/6 plus 9/6, giving us 73/6. Now 73/6 is 12.16666, repeating. But we know the square root of 64. The square root of 64 is 8. And look at that. That's pretty far off now. All right. So the point here is that for approximation to actually be a good approximation, we want to make sure that we stay relatively close to our point of tangency. All right. Now in here 10, that's still not that bad. 64, that's pretty far off from that 9. All right. So that's why we're pretty off here. Let's do another example. B. Let's see. Let's say that I have now, so same instructions, but now I have f of x is equal to the cube root of x, and we're gonna approximate the cube root of 26. All right. All right. So the cube root of 26. 26 is not that far off from a perfect cube. The perfect cube that I'm thinking of course, being 27. So if I look here at, well, what would be f of 27? So the cube root of 27, that happens to be 3. All right, so this gives us a point 27 comma 3, which we can do our linear approximation based on. All right, so what was linear approximation? F of x is approximately f of c plus f prime of c times x minus c. All right, and what would that be in this case? Well, that would be f of 27, right, because that's where we're basing our approximation, times f prime of 27 times x minus 27. All right, so we know what f of 27 is, right? It was 3. So we got that part. But f prime of 27, so let's see. Let's do some side work. We know that f of x is x to the 1/3. Then f prime of x would be 1/3 x to the negative 2/3. In other words, 1/3 times x to the 2/3. All right. Now, that's for just f prime of x, but I need f prime of 27. So f prime of 27 would be 1 over 3 times 27 to the 2/3. All right, so in here, 27 to the 2/3. Well, let's do the 1 to the 1/3 first, right? Because to the 1/3 will be a cube root, and the cube root of 27 is 3. And now the squared, 9. And then times 3, 27. So I end up with 1 over 27. So now, what do I get? F of 27 was 3 plus f prime of 27 was 1/27 times x minus 27. Distribute 3 plus x over 27 minus 1, right? And combine like terms, x over 27 plus 2. So what we found here is that f of x, well, it's approximately, not equal. F of x is approximately x over 27 plus 2. So now let's figure out what f of 26 is approximately. All right, so f of 26, which again would be, for this case, the cube root of 26, will be approximately 26 over 27 plus 2. And now that 2, that's the same thing as saying 54 over 27, right? And at that point, 54 over 27 plus 26 over 27 is 80 over 27, which if you plug it into the calculator, you'll see that this is 2.9629629, repeating, right? Essentially, those first three digits repeat. 962, 962, 962. All right. But what is the actual cube root of 26? The actual cube root of 26 is 2.962496068. So in here, we see that our approximation was actually pretty good still, right? 2.962, 2.962. 3 decimal places. Well, yeah, because 26 is pretty close to 27. But what if you got a bigger value? For example, let's do f of 125, right? So in here, what I'm asking for is the cube root of 125. So let's see. We would say that this would be approximately, well, x over 27, so 125 over 27 plus 2. So that'll be 125 over 27 plus 54 over 27, giving us 179 over 27, right? And at that point, 179 divided by 27 gives us approximately, or actually I should say, it equals 6.629629629. So that repeats, all right? But what is the actual cube root of 125? It's 5. So in here you see that right away, this is not a good approximation, right? And why would it be a bad approximation? Well, because again, 125 is pretty far from where we approximated at 27, right? So, all right, so now, visually, what's happening here? So, or why are they so far apart? So if I look at the cube root of x, right? The cube root of x looks something like that. And if I look at a tangent line here, right? This line is just going off that way, and look how far apart that is already. So if this value right here happens to be that 27 that I did things at, well, 125 is going to be like over here, and that distance is going to be even bigger now between the function and the line. All right, so now let's do other applications of this. Actually, before we do applications, let's look at differentials a little bit more deeply. So let's look at a definition of differentials, and let's write in white. All right. So differentials. Let y equal f of x represent a function that is differentiable on an open interval containing x. The differential of x, denoted dx, is any non-zero real number. All right. And here, when we say any non-zero real number, we mean something that is infinitesimally small. Infinitely small. There we go. But I mean infinitesimally small, right? Like 1/1,000,000, or 1/1,000,000,000, or 1/10,000,000,000, right? So something super tiny. Um, so that's what we mean by the differential of x. All right. The differential of y denoted dy is equal to f prime of x dx. All right. So that's the differential of y. dy is equal to f prime of x dx. Now let's see what we're talking about here visually. All right. So let's look at a curve and the tangent line once again. So let's say I had this curve, right, and the tangent line, and let's say that it's off of there. Let's try that again. Okay, cool. Now, in here, this point right here, let's say that is at x. And let's say that about here, this is, well, let's call this distance delta x, the change in x. And this here will be x plus, actually, let's not use x, let's use c, just to talk about a very specific value, c. C plus delta x. Okay, fine, cool. Now, in here, this is at the height of f of c, right? This point over here, and perhaps I should color coordinate this a little bit better. So that's at the height of f of c. This up here is at the height of f of c plus delta x, right? Because that would be the coordinate there. Now, in here, let's look at this point over here. This point is at the height, well, let's see. If I call, so in here, our blue function, our blue curve is f. If I call our tangent line there, let's call it g, all right? So in here, this height, well, this is still the same as g of c, right? They're both at the same height there. But over here, this is at g of c plus delta x. All right, now let's get a little more things in here. Let's figure out what the equation of this line is. All right. So in here, let's figure that out. Well, normally we would say y equals, but in here, because I'm using the function g, or the name g for this function, I'm going to say g of x equals, well, I'm going to write it as f of c plus f prime of c times x minus c, right? And in here, what would that be? Well, let's just leave it at that, right? Because we don't actually have any values here. Now, this is our slope, right? This is our function there. Now, in here, if I talk about what this height is here, that's when I plug in x, that's when I plug in c plus delta x. So g of c plus delta x, right, because I want to figure out what this height is, that would be f of c plus f prime of c times c plus delta x minus c. And why do I want that? Well, now this can be now f of c plus f prime of c times the c minus c cancels out, so delta x. I'm going to take out those parentheses there. Now, that's this value, right? That's at this value. That there, that tells us this height, right? This here is this height, f of c, or g of c, f of c. And, well, if this entire thing was g of c plus delta x, right? This piece right here, which instead of writing g of c plus delta x, maybe I should say this thing. F of c plus f prime of c delta x. And if I want to figure out what this height is right here, notice that this thing right here was f of c plus f prime of c. This piece right here, f of c. So the difference there would be subtracting those two, giving me that this height right here is f of c. Perhaps I should write smaller there. And there's really f prime of c times delta x. Right, that's that height there. Why do I care about that? Well, notice here that this height over here would be given, again, y was f of x, right? Y was f of x. So in here I can say that this is delta y, right? The change in y. So the change in y going from this point to that point. So that's that, the change in y. This right here is the change in y along this tangent line, right? If I let here this delta x, if I let that go to 0, essentially, or excuse me, not really going to 0, but let it go to very, very, very small, all right, that becomes a differential. So in here, we can rewrite that now as, well, this piece right here. And perhaps there we go. So this would be now f prime of c dx, all right? But now, this over here on this side, I'm going to call this dy. So I'm defining dy to be f prime of c. Well, in here, that's just for the specific c, but in general, f prime of x dx. And that represents here the change in height over an interval of delta x or dx, right? So a very small distance over in change in x, a small distance in change in x. We got to figure out, well, excuse me, this represents how much the tangent line has changed versus delta y representing how much the function has changed. All right. Now, so notation here, I'll say when delta x is tiny, we denote it dx. All right. So when we talk about a differential, we're saying that a differential is a tiny change. All right, an infinitesimally small change. So now, let's see how this can be helpful now. So example C. If I have this following function, so compare delta x, excuse me, delta y, and dy with the information given. All right, so let's see. Let's say that we have this function y equals x cubed. Let's say that x equals 1, and the change in x that we're going to consider here, which would be equivalent to dx in this case, let's see that it's 0.1. All right. Now we're trying to figure out what the difference between delta y and dy. or we want to compare them. So in here, well, what's delta y? Delta y is y sub 2 minus y sub 1. All right, what does that mean? Well, if I'm starting at 1, right, and I'm talking about the change in x being 0.1, well, I'm going to go to, so this is x of 1, my x of 2 is going to be 1.1, right? I'm just adding 0.1 to it. So what I'm really saying here is, well, my y sub 2 is going to correspond to this, so it's going to be 1.1 cubed, and then we have that times 1 cubed. And then 1.1 cubed is 1.331. 1 cubed is 1, so we end up with delta y being 0. Well, hold on. I don't know how I went from a minus to a plus here. There we go. 0.331. All right, that's delta y. That's how much the y values have changed from from x being 1 to x being 1.1. But now let's look at the differential there. The differential here, we know it's f prime of x dx. And well, what does that tell us? Well, let's figure out what f prime of x is. And here f prime of x is 3x squared, so we get 3x squared dx. So now let's figure out what happens when we plug in our values here. So x was 1, so we get 3 times 1 squared, and dx is our differential there. Let's say that's 0.1, and that gives me, well, 0.3. All right, 1 squared is 1 times 3 is 3, 0.3. Now what did we find here? Well, what we found here is that even though the y values have changed a total of 0.331, right, over the function over the curve, along the tangent line, the y values have only changed by 0.3. All right, so not as much. All right. Visually speaking, let's see. What do we have there? Visually speaking, if this is, so the function was x cubed, right? And this is what x cubed looks like. And let's say that here is 1, and I'm going to exaggerate this, but see, let's say that here is 1.1. And that's our point of tangency at 1, right? So that's the line that I'm comparing it to. Now in here, well, what we're saying here is that if I look at these, let me draw that blue curve a little bit better. There we go. Way better. All right. So in here, if I look at this in here, right? This is delta y, whereas this is dy, right? How much the tangent line has changed in that interval, right? Versus how much the function has changed in that little interval. So now let's see an actual application of this, all right? So we can see how this is used. And let's not write in yellow. All right, so here we go. D. The measurement of the side of a square floor tile is 10 inches. With a possible error of 1/32 of an inch. All right, so our measurement, whatever we use to measure it, has an error, approximate error of 1/32 of an inch. So now, here's the first question. Use differentials to approximate the possible propagated error in computing the area of the tile. All right, so what is it saying, bro? Let's think about what we have here. Actually, I'm gonna. There's two questions. That's the first one. So the next question is, um, calculate the percent error. Calculate the percent error in computing the area of the tile. Computing area of the tile. All right. So what do we have here? We've got some tile, right? And we measure this to be 10 inches and this to be 10 inches as well, right? It's a square tile. So in here, well, this is 10 inches, but we're 1/32 of an inch off. So the question is, if I wanted to figure out the area of this tile, how off would I be? All right. That's essentially what we're asking here when it says calculate the percent error. How off would I be? Well, let's figure out first what the propagated error would be. So here we go. Number one. The propagated error essentially here is talking about the differential. All right. So if I use, well, we have our area. So we have an area, right? We're trying to figure out the area. So we're going to start with our area formula. So area is equal to the side squared. What else do we have? We have that the measured side was 10 inches. And what else do we have? We said that the possible error would be up to 1/32 of an inch, right? Technically plus or minus, all right? And I'll put them in yellow. Technically plus or minus because we don't know if we're over measuring by 1/32 of an inch or under measuring by 1/32 of an inch. So we'll keep that in mind, but that's not really going to change anything in our calculations. It's just something to keep in mind. So I'm not gonna add that until the end. Now, in here, this delta x can be considered to be dx. All right, and now, well, what do we want? Let's see. If I take the differential of the area, that's going to give us 2s ds. All right, and now if I plug in the things that I have here, I have 2 times 10 times 1/32, right? And again, technically plus or minus. But now, 2 times 10, well, the 2 becomes a 1. It reduces with 32, making it a 16. 10 is divisible by 2, it becomes a 5. 16 is divisible by 2, it becomes an 8. So I end up with overall 5/8. And this is talking about our the area, so it's square inches. So what we're saying here is that the measurement could be up to 5/8 square inches off. All right, the area itself. Now, how much of a percent error is that? All right, so let's see. That's part 2. So in here, yeah, so we found is that the propagated error is up to 5/8 of an inch. And in decimal, this is, so we're saying plus or minus 0.625, all right, square inches. Now, well, in percent error, to calculate the percent error, we would have to do the measured error, like the measured, versus the actual area. So our measured would be that, like our error, right, over the total area. So our measured error would be, well, I want to use 5/8 actually. I want to use 5/8 over the total area, and the area here would have been 10 squared, right? If it was truly 10 inches, it would be, the area would be 10 squared. And what does this give me? Well, this gives me 5/8 times 1/100th, right? And from here, 5 is divisible by 5, 100 is divisible by 5, and I end up with 1/160th, right? 8 times 2 is 16, so 8 times 20 is 116. This, so, and remember this is all plus minus, so this gives me essentially 1 over 160, that's what our percent error is. But what is that as a decimal? That would be 0.00625. All right, that's technically plus or minus. But so this is our relative error. Now in here, Let me see, I'll say that again. This is a relative error, but I want that relative error as a percent. So that tells me now that the percent error would be 0.625%. So that's a very small error, right? Less than 1%. Um, but in here, yeah. So we found there is the error in calculating that area of that tile. So all right. So next one, let's do another similar one. E. So a sphere's radius is measured as 8 inches with a possible error of 0.02 inches. All right. So again, we're going to use differentials. Use differentials to approximate the propagated error in computing the volume of the sphere. Right? And 2, just find the percent error. Alright. So, alright, so here we go. A sphere's radius. Alright, so we're working with a sphere. So here's our, oh, that's that awful looking sphere. Let's do it better. Way better. So that's our sphere. Right? And what we're saying here is that we measure the radius from the center to the edge. We measure that radius, and our radius was 8 inches. Our possible error of the radius, in other words, our possible error was 0.02 inches. And in here, what are we trying to figure out things with? Well, we're trying to figure stuff with its volume. So the volume is 4/3 pi r cubed. All right, and that's a 3. All right, so let's figure out the differential here, right? Because we want to figure out what possible error we can get here. And our differential is going to be 4 pi r squared dr. All right, bring the 3 down, that one cancels out, subtract by 1. And now, well, what does that give us? That's going to give us 4 pi times 8 squared times 0.02. Let's change that. That's 2/100, right? Because of the 2 decimal places, which is 1/50. All right, so I'm going to write that as 1/50 over here. And what does that give us? Well, the 4 reduces, it becomes a 2. The 50 reduces, it becomes a 25, right? They were both divisible by 2. After that, nothing else really changes. So now 8 squared, 64. 64 times 2 is 128. So I end up with 128 pi over 25. So that's our possible error, right? Our possible error in their volume is that much in cubic inches. Well, what does that mean? So that's kind of hard to visualize. So that would be, so essentially we're saying that we'll be up to 16.085 cubic inches off, all right, by just being 2/100ths of an inch off in our radius measurement. So let's see what percentage that is. All right, what percent error is that? I don't know why I wrote 3. 2. So, well, first we need to figure out the actual volume, right? Because we need so what we need is the differential over the actual volume. So this is the measured error over the total volume, and that would be, well, we already know what dV is. I'm gonna use a fraction. 128 pi over 25, right? And what was the actual volume? Well, the actual volume, let's see. We had 4/3 pi r cubed, and the volume that we measured was with 8 radius, right? The radius was 8 inches, so 4/3 pi times 8 cubed. All right, so 8 cubed times 4. 8 cubed is 512. 512 times 4 is 240. Excuse me, 2048. So I end up with 2048 pi over 3. Now, from there, what do we get? Well, let's see. That's the denominator. 248 pi over 3. And perhaps I'll move this to the side because it was side work. All right. And I'll also change the color. Now, in here, let's reduce this fraction, right? Because in there we have a fraction over a fraction. So let's see what we can do now. A fraction over a fraction. So a division turns into a multiplication by the reciprocal, right? 2048. All right. At that point, we see, well, this pi and this pi cancel each other out. 128 and 2048, they're both powers of 2. So that tells me that 128 definitely goes into 2048. So 128 goes into itself once. 2048, let's see. 2048 divided by 128 is 16. All right. You could think of these as powers of 2. This is 2 to the 2 to the 11. This is 2 to the 7. So it would be, the difference would be 2 to the 4th, which is 16. All right, so now what does that give us now? We end up with 3 over 25 times 16. Well, multiplying by 25 is very easy. Think of quarters. If I had 16 quarters, how much would that be? Well, that would be $4. So I end up with 400 as our denominator. All right, that's 3 over 400. Now, as a decimal, this is 0.0075. All right. That's also very easy to do because I had, if you look at 3/4, right, that's 0.75, and then the extra 2 zeros bring it over a little more. But anyway, now from here, what is that? That's our measured error, right? What is the actual percent error? So the percent error would be, well, this as a percent, so 0.75%, which again is not that much, right? It's less than 1% off. So even though this 16 cubic inches sounded like a lot, well, it's because it's a volume, it's less than 1% off. So that measurement of 8 cubic inches is a pretty good, excuse me, the 8 inches for the radius, it's a pretty good measurement for the sphere. All right, so now let's get some practice in just calculating differentials. All right. And I hope you notice how I was doing them, specifically in how I was calculating them, right? Because, well, maybe I'll remind you of this. So we said that dy is equal to f prime of x dx, and notice that all I was doing was finding the derivative of the function that was given and then writing a dx at the end, right? Because that's the definition. So if I had something like, so if I said find the differential of these, so find the differential. And I had y equals x squared. Well, then dy would just be 2x dx, right? The derivative times dx. If I said y equals the square root of x, which is the same thing as saying x to the 1/2, then our differential would be 1/2 x to the negative 1/2 dx. If I said y is equal to cosine of x, then my differential would be, well, the derivative of cosine is negative sine, so negative sine of x dx. if I had something like y equals x squared times e to the negative x, well, the differential is, well, f prime. In here, that means we have to take the derivative, right? And look at that. We've got a product of two functions. So we need to use the product rule. So we're going to say it's going to be the derivative of the first times the second plus the derivative of the second, negative e to the negative x times the first. And then all of this dx. If you really wanted to, you can really rewrite this as e to the negative, excuse me, x e to the negative x times 2 minus x dx, right? But again, it's just finding the derivative, right? And then writing a dx at the end. If I had y equals 1 over x squared, well, that's the same thing as saying x to the negative 2. So our dy would be, well, negative 2x to the negative 3 dx, which I can rewrite as negative 2 over x cubed, right? Let's say I had y equals tangent of 3x. Then dy would be 3 secant squared of 3x dx, right? And I mean, the same just goes on for whatever the function might be, right? For as far as the differential goes. If I had, let's see, let's complicate this a little bit. X to the third plus 2 to the 1/2, right? Then dy would be, well, the differential here would be 1/2 times x to the third plus 2 to the negative 1/2 times 3x squared dx. So what does that give us? Let's reduce this a little bit. I end up with 3x squared over 2 times x cubed plus 2 to the 1/2. All right. If I have, I don't know, secant squared of x over x squared plus 1, then what would dy be? Well, here now I need the quotient rule. So let's see. The derivative of the top, 2 secant x times secant x tan x, right? Because I have something squared. So bring the 2, and then by the chain rule times all that. So the derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom. Oh, hold on, I forgot to multiply times the top there. Oh, no, I did it. The derivative of the bottom times the, let's go. I confused myself for no reason there. Anyway, so all of this dx, right? This dx is right here. So let's see, how can we reduce that? I see they both have a secant squared. So we have secant squared of x times 2 tan of x times x squared plus 1 minus, I took out just the secant squared, so minus 2x. I guess I could have taken out a 2 as well. Minus x. Alright. Over x squared plus 1 squared, and then dx. Alright. But I mean, like, again, this is just finding the derivative and then multiplying by dx on the outside. We already know how to find the derivative. Alright. So that concludes 4.8. Right? That is the end of 4.8.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.